All right, hello everybody. Today we're moving on basically one step up from the spectrum of a matrix to something that's incredibly useful in linear algebra, and that's called the Jordan form. And this is, you probably encountered your spectrum in your actual linear algebra course, and it probably would have just been called the eigenvalues at the time, but now I think we're getting outside of the range of linear algebra, at least the one semester that you've likely taken. So this thing called Jordan form is a really special kind of representation we can put matrices in. And I'm going to start it out with something that should feel very familiar with you, and that is the diagonalization of a matrix, right? So I think most of you have probably seen this, that if you have a matrix n, that's n by n in rows and columns, and we have n linearly independent eigenvalue pairs. And I'm just going to pair them together in a set here. Then what I can do is I can form a matrix X, capital X, from these linearly independent eigenvectors. And there I'm just making explicit how I formed my matrix from the linearly independent eigenvectors. And once I've formed that matrix, it turns out that taking X and then a diagonal matrix where all of the eigenvalues are down the diagonal, if I take X from up here, times the diagonal matrix times X inverse, then I recover my original matrix M. And actually I could write this alternatively as X inverse M X is diagonal. This would basically be the diagonalization of M. And it diagonalizes into the eigenvalues. So I think that's covered in most linear algebra courses. So this is interesting because this is actually an if and only if statement. So that means the reverse is true. If you can find a matrix X, if I can just find some matrix, I don't know anything about its columns necessarily, but if I can find a matrix which diagonalize and the diagonal D for which this equality is true, then necessarily the vertical components of the vector X, or the matrix X, will be eigenvectors. Okay, so I've provided an example for this. So in our previous section, we saw this matrix, 1, 2, 0, negative 1, and we found some eigenvectors, 1, 0, and negative 1, 1. And now we're just going to see that, in fact, if I define a capital X in this manner, then we recover the diagonal matrix D. If I act X inverse MX together, I recover the diagonal matrix with entries which were my eigenvalues. So my eigenvalues for the matrix M were precisely 1, negative 1, and the eigenvectors were exactly this 1, 0, and negative 1, 1. All right, so here's probably the important thing about this section, and I don't think it's stressed enough. So unfortunately, not all n by n matrices necessarily have n linearly independent eigenvectors. This is the entire reason why we have kind of linear algebra as a whole. If we could diagonalize everything, then we could actually solve basically all problems. So this is kind of an unfortunate occurrence, and I've provided an example here. So let's look at this matrix. 3, 4, negative 10. 2, 1, negative 2, 2, 2, negative 5. And I really want you to focus on this matrix because we're going to be using it all day today. This is the matrix we want to use all day. If I form the characteristic equation of this matrix, then I recover and factor it. Then I recover lambda minus 1 and lambda plus 1 as factors. But notice the power here, 2, means that lambda equals negative 1 is a root of multiplicity 2. And just because we have a root of multiplicity 2 does not necessarily mean we won't be able to find 3 linearly independent eigenvectors, but it should send alarms to us. Sends alarms that maybe there are only 2 eigenvectors. This is because really there are only 2 roots, right? We're only able to find 2 roots of the equation. One of them has a higher multiplicity. If we go through the regular procedure and search for eigenvectors, we can find them. And we would notice that there are, in fact, only 2. So there are only two linearly independent eigenvectors. And in particular, this means that M can't be diagonalized. So M's a 3x3 matrix, but it cannot be diagonalized. So we have to come up with, and mathematicians as a whole have come up with, the next best thing. So what is the next best thing to diagonal? It turns out that we can find these things called generalized eigenvectors. So a generalized eigenvector, we're going to generalize the eigenvalue equation by including a power. So this is my eigenvalue equation, but I'm going to include a power k here, and that's what makes it general. So if I have a lambda, which is an eigenvalue, then a generalized eigenvector of rank k, so this is very important, rank k is always included with the generalized eigenvector. And that vector satisfies my eigenvalue equation, but now I have a power of the matrix. And necessarily for rank k, I know that if I subtract the power of the matrix by 1, I can no longer satisfy the eigenvalue equation. This is what makes it specifically of rank k and not rank, if I was of rank 3, we wouldn't want this to be true for when k was 2 as well. Then it would kind of reduce to the rank 2 case. So we want to keep it separate so that it works when I take k powers of my matrix, but it doesn't work when I take k minus 1 powers of my matrix. Okay, so here's a really good proposition that's very useful for us and all of mathematicians. For every n times n matrix, there exists n linearly independent generalized eigenvectors. Okay, so no matter what matrix I choose, I can always find a collection of linearly independent generalized eigenvectors. And that's what's going to give me the next best thing to diagonalization. There's a corollary that's part of the proof, and that's what says that generalized eigenvectors have rank at most to the multiplicity of their associated eigenvalues. So what that's telling us up here in this case is that for my generalized cases, I can have at most one eigenvec, say eigenvec of rank 2, and then I'll have 2 and 2 gen eigenvec of rank 1. And the reason why we gain the 2 of rank 1 is that a rank 1 generalized eigenvector is the same thing as just an eigenvector that's not generalized. So that's where my 3 will show up. I'll be able to find basically one more eigenvector corresponding to lambda being -1. It just so happens that will be a rank 2 generalized eigenvector. Okay, so I emphasize that in this remark here. I say searching for generalized eigenvectors. So because of that corollary, we only want to choose eigenvalues with non-trivial, meaning greater than 1 multiplicity, to try to find these generalized eigenvectors. All of the eigenvalues with multiplicity 1, we will necessarily be able to find at least one traditional eigenvector for. Okay, so let's jump back to this example where our matrix has these 2 eigenvectors, but we want a third, right? More or less what's going on is we have found 2 eigenvecs, but we want 3 for, and I'm putting it in quotes now, diagonalization, even though we're going to find out that it doesn't quite diagonalize. It's something similar, but not quite. So we want 3, so we must search for one generalized eigenvec. Okay, we need to go searching for one generalized eigenvector. Necessarily it has to be this one because that was our lambda with multiplicity 2. Okay, so let's try to find it. What we do to find something with multiplicity 2, or rank 2, right? A rank 2 generalized eigenvector means we're going to take our eigenvector equation and we're going to take it to the power 2 instead, which there's my eigenvector matrix and my possible eigenvector. And I took it to the second power and I set it equal to 0, 0, 0, just as the eigenvector equation would normally be. And what we recover out of that, if I simplify my matrix, is this matrix, which we see is 4, 4 minus 8, 8, 8 minus 16, and 4, 4 minus 8. This looks like a very degenerate matrix, and they always will. These matrices, when we take them to powers, are going to become more and more degenerate as we take higher and higher powers. So really this reduces, this matrix vector equation that I have here, all the way equal to 0, reduces to one row. Only one row is giving me any information. And that row is basically saying 4x1 plus 4x2 minus 8x3 is 0, or if maybe I solve for x3, that x3 is half x1 and half x2. So if I make that substitution into my generalized eigenvector, I'm going to substitute x3 with its definition up here, and there you go. There's that definition, 1 half x1 plus 1 half x2, and I gain x1, x2, 1 half x1 plus 1 half x2. Now this will be a generalized eigenvector for any non-zero choice of x1 or x2, just like our eigenvectors were true eigenvectors for any choice of a single x. However, we actually have a second equation which helps us out here, and that's that we need a linearly independent generalized eigenvector. And linear independence means that whatever we choose here for our generalized eigenvector cannot be dependent to the eigenvector that we've already found, which was -1, 1, 0. So to make that true, that they're linearly independent, I need to make sure that this, which is saying x1 equals x2, I don't do that up here. Don't let x1 equal x2. Okay, so a good choice for that is this one right here. So we're just going to let x1 be 2 and x2 be 0, which gives us the generalized eigenvector of rank 2 associated to lambda being -1 of 2, 0, 1. Okay, so now we actually have 3 linearly independent generalized eigenvectors, 2 of them being true eigenvectors, but we do have 3, and that's what we're looking for. Okay, so now I really, this is, I can't stress this enough. The following theorem and definition is the most important theorem in linear algebra pertaining to ODEs. So when it comes to ODEs, which is the entire point of this class, there's one theorem in linear algebra that trumps them all, and that's this one. And this is the next best thing to diagonalization. Okay. So we have the definition here of what we call a Jordan chain. So recall I have these things, these generalized eigenvectors, and I'm going to give myself a set that contains a lot of them, which increase in rank. These are the rank. Ranks increase, but lambda, if we look at lambda, each lambda is the same. Okay, so Jordan chain says multiple generalized eigenvectors corresponding to the same eigenvalue. Okay, so however many we can find for any associated eigenvalue, we're gonna push them together in a chain. And in particular, this chain needs a very special property, and that property is that for every generalized eigenvector in the chain, right, there's a generalized eigenvector. If I act the matrix, the eigenvalue matrix, on that generalized eigenvector, it outputs previous elements in the chain. Okay, so that's why this is called a chain, because every time I act this matrix, the eigenvalue matrix, on the generalized eigenvector in the chain, maybe this top one, it shifts me down the chain by one element. So it's going to take me from one generalized eigenvector to the next, and at each step it's reducing the rank of the eigenvector. So each step back reduces the rank of the eigenvector until we get to the first one there. Okay, so this set, it's just a set of eigenvectors associated to the same eigenvalue with special ranks that keep increasing. That's called a Jordan chain, and I've added that it has a specific length here. The length is just the size of the set. Okay, I know this is a really, really complicated definition. This is probably one of the most complicated definitions in the entire semester, so I'm just going to pause right here. You can take some time to stare at it, and if you want to pause the video, take some time to stare at it a little longer. It's a very important definition. We can definitely talk about it in class too. but we need to understand this a little bit. Okay, hopefully that gave you enough time to pause if you needed to. Now we're going to look at the example where we construct a Jordan chain. This will make your life a little bit easier. So we have this matrix from the previous example, right? And we had two eigenvectors, true eigenvectors, and then the second one had multiplicity 2, the eigenvalue. So we found a generalized eigenvector of rank 2, which was 2, 0, 1. We have to note now that, theoretically what we want to do here is these should be grouped. These should theoretically be grouped into a Jordan chain, but if I act the eigenvalue matrix on my generalized eigenvector, I gain twice the original eigenvector. And that's totally fine, but I just have to account for the 2. We have to account for the 2 in the Jordan chain. Okay, that's what makes it truly a chain and not just a collection of generalized eigenvectors. The chain needs to account every time the eigenvalue matrix is acted on the generalized eigenvector. It needs to exactly output the next element in the chain. So if that's the case here, then my Jordan chain on -1 for lambda being -1, the last element is my generalized eigenvalue, and then the action of the eigenvalue matrix has to take me to the previous element, and so that previous element is actually twice the eigenvalue that I saw before. Not a huge deal, but we do have to keep track of those coefficients. And then I also technically have a Jordan chain corresponding to lambda equals 1, it's just that my Jordan chain is only one element long. All right, let's move on from there and define this next piece called a Jordan block. So a Jordan block is a very specific matrix associated to a Jordan chain. So it's a specific matrix associated to a Jordan chain. And more or less, what's going on is that we have a Jordan chain associated to lambda I, right? Associated to some very specific eigenvalue. And it has a very specific length, mi. Okay, so in that case, mi here is 2, because there are 2 elements there. Mi here is 1. Lambda I here was 1. Lambda I here was -1. And all this is a very particular matrix where it's necessarily mi by mi in size, it's square. The diagonal perfectly has the eigenvalue on it. And the first off diagonal to the right, so the upper right off diagonal, has 1s in it. So it's a very specific matrix where the diagonal is all lambdas, and the very first off diagonal is a 1. This is called a Jordan block. Okay, so then let's continue with our example on the Jordan block. So here we have our matrix M. Here's our first Jordan chain. Here's our second Jordan chain that we constructed from the previous example. And now we can form Jordan blocks. And the first one looks kind of funny because this is a 1 by 1 matrix, since the Jordan chain was only 1 element long. And the second case even doesn't look that terribly special because it's a 2 by 2 matrix, so we don't see any upper right zeros, since Jordan chain was 2 elements long. Now what you can see, right, so I'm highlighting the 1 by 1, 1 by 1, 1 element long, 2 by 2, 2 elements long. then the last thing that's important about these is that the diagonal, which understandably there is just a 1, the diagonal over here is -1. These diagonals exactly correspond to lambda, to the eigenvalue. So those are the Jordan blocks. And finally, we get to this theorem. Okay, so this theorem is really tricky, kind of. It's notationally heavy, or it's even verbally heavy. It's verbose, but it's important. So basically, what this says is that the next best thing to diagonalization is Jordan blocks instead of diagonals. Okay, because what's going on is we're going to do the same thing that we did for diagonalization. If I have a Jordan chain, so I'm going to grab my Jordan chain, and for each Jordan chain, I'm going to construct a matrix. X sub lambda I. That's the Jordan chain associated to the very specific eigenvalue lambda I. It's going to be the vectors in the Jordan chain, and they're going to construct a matrix for me. Now let's notice really quick the size of this matrix. It's n tall, but it's only mi wide. Maybe I'll make that clear here. N entries, so that's the full length or full height, but it does not have full width. It has mi entries, aka length of Jordan chain. Okay, so the entries horizontally are only corresponding to the length of a given Jordan chain. What I have to do on top of that to construct a so-called diagonalization matrix is I have to then link all of the Jordan, I don't even know what to call these matrices, these X lambda I matrices. I'm linking those together, right? Once I link those together, I know that the sum of all of these mi's, or the lengths of all the Jordan chains, have to add up to n. So once I link all of those together into capital X, this will have length n. And that's where I'm going to construct my n by n matrix. So it's n by n. So that X will necessarily be my n by n matrix. Okay, now this X that I've just constructed is my so-called diagonalization X, but you've noticed that I haven't placed a D here. This is J, not D, because not quite diagonal. The next best thing, that's what we can think about. So matrix M is xj, x inverse, not quite diagonal. The matrix J is diagonal-ish. It's diagonal in blocks. So if I restrict to the Jordan blocks, which I defined earlier, right? If I restrict to these Jordan blocks, which I defined earlier, these lambda i's, each of the lambda i's are almost diagonal. Every single one of these is so close to being diagonal, but not quite. Then what I end up with is J being almost diagonal, but not quite. All right, so now let's finish this off. So if we recall from the previous example, in our examples here, we have the Jordan blocks corresponding to this matrix, and we also have our Jordan chains with their specific generalized eigenvectors. I can construct capital X from the collection of Jordan chains, right? This was the first Jordan chain, and then these two formed the second Jordan chain. I put those in as vectors, and what I recover is a pseudo-diagonalization theorem where M can be represented as this nice capital X inverse, and then my Jordan blocks. So if we look right there, the top left corner was the Jordan block corresponding to lambda equals 1. And then the bottom right corner is the Jordan block corresponding to lambda equals -1. And so you'll notice we can still read off the eigenvalues from the diagonal, but we have to put up with these little off-diagonal terms in just some of the cases. So equivalently, we can write it like that. All right, that's all I have. I know this was a really crazy lecture, but I hope you enjoy it, and it's really a cool topic in linear algebra. Let's talk more in class. See ya.